Every leading comet researcher is in agreement. 3i Atlas is acting unlike anything they've ever encountered. Whilst this mysterious traveler from the stars heads toward its fated meeting with Mars this October, it's undergoing transformations that defy every established model. Its glowing green shroud has expanded so far across space that it now surpasses Jupiter's vast diameter. Its brightness doesn't rise steadily. It surges unpredictably, almost as if it has a will of its own. Its tail ignores the usual rules of solar wind dynamics, while the way its dust reflects sunlight has never been recorded in astronomy before. As it closes the distance to the red planet, the comet appears less like a product of natural forces and more like something deliberately crafted. But what makes this story even stranger is the silence surrounding it. While amateur skywatchers all over the globe share their shaky images online, the heavyweights of astronomy, the Hubble Space Telescope, James Webb, and Gemini, have all gone quiet since late August. Not a word. Tonight we're diving deep into this cosmic enigma. Stay with me until the very end, because 3i Atlas isn't just misbehaving, it's raising questions that scientists and officials aren't openly addressing. Back in early September 2025, something occurred that astronomers weren't anticipating. At a distance of around 2 astronomical units from the Sun, Atlas suddenly lit up with a speed no prediction had accounted for. The big question now echoing through observatories is painfully simple. Why? To understand the magnitude of this anomaly, you have to picture the science of brightness predictions in everyday terms. In essence, a comet's light curve functions like a cosmic weather forecast. Astronomers can project exactly how luminous it should become as it warms up on its approach to the Sun. These forecasts don't come from intuition. They're based on decades of cometary records, detailed equations about how frozen materials vaporize in space, and precise measurements of how stray dust scatters light. For weeks, 3i Atlas was right on track. Its glow steadily climbed at a pace that lined up perfectly with the models. Professionals and amateurs alike logged the same numbers, confirming it was behaving as expected. The comet's increasing radiance made perfect sense. More heat meant more outgassing, and more gas and dust meant a thicker glowing halo. Then, between September 7th and 15th, the curve broke. Observers began reporting brightness levels climbing above predictions. In astronomical terms, Atlas wasn't just drifting, it had jumped onto a completely different track, and the change wasn't a subtle one. On standard magnitude charts, the numbers veered away like a car suddenly stomping on the accelerator after cruising at a steady highway pace. But here's the complication. Astronomers can't even agree on whether this is an actual eruption of comet activity or something more technical, an observational artifact called the aperture effect. To break it down, aperture effect is a fancy name for measurement tricks. Imagine staring at a campfire from a distance while peeking through a narrow tube. You'd only see the core flames and figure it's small yet extremely hot. But open your vision wider, and suddenly you notice the glowing spark stretching far beyond. Different telescopes with different apertures and instruments can make the same patch of space appear brighter or dimmer. And that's the debate: is Atlas putting on a genuine show, or are our tools exaggerating the performance? One of the best ways to track this comet story is through the Comet Observation Database, often called COBES. On those charts, anyone can see the shift. A line that had been climbing steadily suddenly steepens in mid-September. Whatever the cause, the change is obvious and undeniable. And to truly grasp the scale of this cosmic event, you need to consider the comet's velocity. Atlas is racing inward at colossal speeds, tens of kilometers every second, or about 210,000 kilometers per hour. That's fast enough to sprint across an entire continent in under 60 seconds. And yet that's merely its current pace. By late October, at its closest approach to the Sun, an event astronomers call perihelion, it's expected to reach around 68 kilometers per second. That date is etched in calculations between October 29th and 30th, at roughly 1.36 to 1.4 astronomical units from the Sun. To put it into context, that distance places it just inside the orbit of Mars. And this is where things get even more intriguing. On October 3rd, before it reaches perihelion, Atlas will have a near pass by Mars, skimming within 0.19 astronomical units. That's close enough to trigger immense interest from the spacecraft already circling the red planet. Instruments like HiRISE, CASSIS, and HRSC are gearing up to capture detailed images of this rare visitor. For scientists, this is a once-in-a-lifetime opportunity. For the rest of us, it could mean answers or more questions. So what's actually happening out there? In plain English, there are two possibilities. Either Atlas is releasing unexpected amounts of gas and debris that our comet models don't account for, or our telescopes are picking up on a giant extended atmosphere in a way that distorts the numbers, or both things at once. No matter which option turns out to be right, the implications are staggering. This isn't just another frozen rock from the Oort cloud or Kuiper belt. Atlas is only the third interstellar object ever confirmed in our solar system. Its very presence offers a rare chance to learn what materials, physics, and mysteries exist beyond our stellar neighborhood. And yet, instead of revealing answers, it's breaking the rules we've carefully written through centuries of observations. The truth is, our understanding of these interstellar wanderers might be far less complete than we like to admit. Could comets born in distant star systems behave differently than anything native to our own? And if so, what does that tell us about the diversity of planets, solar systems, and unknown forces scattered across the galaxy? The clock is ticking. With Atlas closing in on the Sun, every instrument on Earth, every sensor aboard space telescopes is preparing to measure this cosmic oddity. What they reveal in the coming weeks could alter how we view the universe between the stars. But here's the thing. The unexplained brightening is just the beginning. The atmosphere surrounding this comet's core is swelling at an extraordinary rate, far exceeding what our current physics says is even possible. Part 2 begins with something even stranger. The hazy cloud surrounding 3I Atlas isn't just unusual because of its sudden brightening, it's swelling outward at a rate that flat out breaks the rules of comet physics. To understand why this is such a big deal, you need to know what astronomers mean when they talk about a coma. A coma is essentially a comet's atmosphere, but unlike our Earth's compact, gravity-bound shield of air, a coma is an unruly cloud of gas, dust, and ionized plasma that can stretch hundreds of thousands of kilometers into space. It forms when frozen ices on the comet's surface heat up and transform directly from solid to gas, dragging dust particles with them until they create a massive glowing shroud that often makes the tiny solid core invisible. On August 6, 2025, when the James Webb Space Telescope focused its infrared sensors on Atlas, astronomers found something astonishing. Instead of the usual mix dominated by water vapor, this comet's coma contained an unusually high amount of carbon dioxide. The CO5 to water ratio was unlike anything normally seen, suggesting Atlas either formed in an extremely cold region of its home star system or followed a chemical path very different from comets native to our Sun. Why does that matter? Because unlike water ice, which only starts vaporizing when a comet draws close to the Sun, carbon dioxide requires far less heat to sublimate. That means Atlas woke up far earlier than usual, growing active while it was still deep in the outer regions of our solar system, long before most comets ever begin putting on their show. Follow-up analyses confirmed this with near-infrared spectroscopy, revealing that its carbon dioxide-dominated envelope wasn't just large, it extended up to 700,000 kilometers in diameter. That's nearly half the size of the Sun. To be fair, that number comes with uncertainties, since different instruments and methods can produce slightly different results, but even conservative estimates point to a coma of staggering proportions. Meanwhile, the Hubble Space Telescope offered a different clue during an observing run on July 21st. Its data confirmed that the comet's true nucleus is tiny compared to its enormous halo. By analyzing the light curve through brightness models, astronomers placed the maximum radius of the solid core at just under 3 kilometers. This confirmation immediately dismissed many of the exaggerated reports circulating on social media, claiming a monstrous comet dozens of kilometers wide. The Vera Rubin Observatory's survey also backed this up, suggesting the nucleus measures somewhere in the 3 to 5.6 kilometer range, though researchers are quick to emphasize how tricky those measurements can be. In all likelihood, the solid heart of Atlas is small and consistent with ordinary comets. It's the surrounding coma that makes it extraordinary. To understand that expanding envelope, astronomers turn to the study of dusty plasmas. Instead of behaving like a simple gas, A dusty plasma consists of ordinary neutral particles mixed with molecules and atoms that have been ionized by intense solar radiation. Once ionized, this material doesn't spread randomly. It organizes into strands and sheets that ripple and pulse like living tissue. Observers who describe Atlas's coma as looking alive aren't exaggerating. They're witnessing the inherent physics of self-organizing plasmas. Charged particles flow along invisible magnetic highways created by natural solar and interstellar magnetic fields, producing filaments and complex shapes similar to auroras on Earth or the towering plasma arcs seen erupting from the Sun. But here's where Atlas defies easy categorization. A gigantic carbon dioxide, heavy coma expanding so rapidly has never been observed in an interstellar visitor before. Consider the pattern. The first interstellar object ever spotted, Oumuamua, showed no visible cometary activity at all. It resembled a barren asteroid. The second, Borisov, acted like a fairly typical comet, complete with a water-dominated coma. Atlas falls between the two, yet apart from them both, burning bright with obvious comet-like activity, but carried by a chemical fingerprint and physical behavior that resist easy explanation. The rapid expansion rate refuses to match our thermal models. Based on how much sunlight Atlas is currently absorbing and using all standard sublimation rates for different ices, the coma's growth speed simply shouldn't be this high. So what could be fueling it? Some have wondered if internal heating from radioactive decay is releasing extra energy, though scientists note that Atlas's small size makes that highly unlikely. Another possibility is that the comet's spin rate is creating stresses and fractures on its surface, exposing fresh ice reserves that react explosively to sunlight. Others propose the comet may harbor exotic frozen compounds unlike anything we've studied before, releasing gases we hadn't planned for. Then there's the plasma interaction itself. When the solar wind, a relentless stream of charged particles from our sun, slams into the comet's ever-growing envelope, it forms what's known as a bow shock, much like the waves generated by a boat cutting across a lake surface. That interaction can accelerate expansion, carve filaments, and produce the shifting, almost organic patterns observers are seeing. Still, even with those explanations, the story doesn't fully line up. Atlas's coma continues to grow faster than models predict, as if it's operating under rules outside those we've grown confident in after centuries of comet studies. The high carbon dioxide content explains part of the mystery, but not all of it. Each new observation only multiplies the questions. If this is what's happening now, while still relatively far from the Sun, what will unfold as Atlas dives even deeper into the inner solar system? And then came another twist, because this comet isn't just oversized, it's not just fast. As summer turned into September, another transformation made Atlas even more striking. Its immense coma began taking on a bright, unnatural green glow that seemed pulled from the frame of a science fiction movie. Part 3 begins with that very glow. Between September 7th and 17th, under the clear eclipse skies above Namibia, amateur astronomers captured images of Atlas that stunned the community. In each shot, the comet shone with an unmistakable emerald aura, a color so bold it seemed painted against the backdrop of stars. Green comets aren't unheard of. This phenomenon occurs when molecules of diatomic carbon made of two carbon atoms bonded together, absorb ultraviolet light from the sun, and re-emit it at a wavelength around 518 nanometers, which human eyes perceive as green. That glow usually happens closer to the sun, when solar radiation breaks down complex organic molecules locked in the ice and releases diatomic carbon into the coma. The intensity and timing of the glow normally scale with sunlight. More heat equals more breakdown, and thus more green light. But that's not what's happening here. Atlas's eerie green gleam is showing up earlier and stronger than models projected, and this doesn't fit the chemistry we thought it carried. Spectroscopic studies revealed Atlas is rich in carbon dioxide, but lacking the typical carbon compounds that usually produce a vibrant green coma. According to the standard playbook, that combination should have caused a delayed or muted green signature at best. Instead, witnesses saw the opposite, a glow both vivid and strangely premature, burning bright at a distance from the sun, where such color shouldn't yet be possible. Scientists didn't hide their surprise when data confirmed what our eyes were already picking up. The comet was turning green far earlier, and far more intensely than its chemistry suggested was possible. On paper, that shouldn't have been happening. Typically, the balance inside a comet's coma is tied to solar heating. Different materials vaporize at different temperatures. Water ice, for example, waits until strong sunlight is absorbed before sublimating. Carbon dioxide reacts much sooner, and more complex carbon-based molecules fragment into simpler ones at varying stages along the journey. So when a comet glows green, it's signaling that carbon chains are being broken apart by solar radiation. The problem with Atlas is that it's glowing green at a stage when the breakdown shouldn't yet be occurring, or at least not this strongly. The implication is unsettling. Either Atlas contains forms of carbon chemistry unfamiliar to our catalogues, or solar radiation is interacting with it in a new, unexpected way. One possible answer lies in the shifting chemistry that takes place as comets heat up. As Atlas gets closer to the Sun, its entire composition is undergoing dramatic changes. Molecules that were once stable in the cold of deep space suddenly crack apart, releasing fresh particle streams that fluoresce differently. The vivid emerald emissions could be a sign of this transformation happening earlier or more aggressively than anyone's models accounted for. It's a reminder that this comet may not be following the same script as those birthed in our local solar system. It's also important to note that the nucleus, the solid heart of Atlas, isn't glowing green. That core is almost certainly a dark, rocky, dirty ice and dust mixture, possibly with red or brown tones that resemble many known comets. The glow is an atmospheric phenomenon only, a light show taking place within the enormous envelope of gases surrounding that small icy body. And here's where it ties back to what we discussed earlier, the possible connection to the brightness anomaly. If Atlas's coma is continually thickening, not only with dust but also with specific molecules like diatomic carbon, then it makes sense that its green hue would intensify. In other words, the strange brightness spikes and the eerie color might not be two separate mysteries, but different signals coming from the same accelerating processes inside the comet. To use a simple analogy, it's like watching neon signs flicker on one by one as a building surges with electricity, all powered by the same unseen current. However, we need to be careful with interpretation. Digital photography tends to exaggerate colors that might appear softer to the naked eye. The bright emerald images circulating online are stunning, but if you look through a telescope, the shade might appear more muted. Still, the data proves that this isn't a trick of the camera alone. The exact wavelength at 518 nanometers has been detected, confirming the presence of diatomic carbon fluorescence in Atlas's coma. Beyond beauty, this glow also serves as a scientific clue. If Atlas is rotating quickly, then different patches of its surface would heat up at different times, exposing new volatile reservoirs unevenly. That variation might explain why observers have reported the green intensity changing dramatically over the span of hours or days. If true, this would imply Atlas's nucleus is indeed spinning and its rotation is directly shaping the shimmering aura around it. Regardless of the mechanism, there's no dismissing the psychological power that comes with something like this. Throughout history, whenever the skies behaved strangely, civilizations reacted with awe, fear, or both. A comet glowing bright green in the heavens, especially one from outside our star system, can't help but fire the imagination. Fiction has programmed us to link green glows with alien technology, signals, or otherworldly presences. Yet nature itself often proves stranger than what storytelling dares to invent. In this case, the glow is real, natural, and chemical, a starborn laboratory unfolding before our eyes. Atlas's exotic materials are being cooked by the sun into dazzling patterns, showing us interstellar chemistry at work in real time. And this is only the beginning. But as Atlas continues its plunge towards perihelion, the higher energy levels from the sun's radiation are expected to rip apart even more carbon-bearing molecules, intensifying the already startling emerald light. The comet could easily transform into an even more dramatic spectacle in October. Amateur astronomers everywhere remain glued to their telescopes, uploading updates almost daily, providing the professional community with constant data points. Together, they're helping piece together the behavior of this interstellar traveler. At this stage, the glow stands out as one of Atlas's defining signatures, and arguably one of the most captivating things about it. But remarkably, the bright green hue isn't the feat that has astronomers truly scratching their heads. As breathtaking as it is, there is something even more disorienting. Atlas isn't just glowing oddly or expanding strangely. It's also breaking one of the simplest rules in the cosmic playbook, the direction of its tail. Which brings us to part 4, the anti-tail phenomenon and a geometry that makes no sense. In Astronomy 101, the behavior of a comet's tail is practically the first lesson. No matter how dramatic the variations, comet tails always point away from the sun. They act like enormous cosmic windsocks, sculpted by the force of sunlight pressure and the constant stream of solar wind particles racing through the solar system. Textbook science explains it well. As the comet approaches the sun, radiation pushes dust outward and creates a curved path trailing behind the nucleus, while the solar wind charges and stretches the ionized gases into a straight beam pointing directly away from the sun. These two tails, the graceful dust curve and the needle-like iron streak, are the defining image of every comet humanity has drawn, photographed, or celebrated for centuries. But Atlas? Atlas gives us something else. Early observations showed a plume of material pointing toward the sun. That's right, pointing in the wrong direction. This bizarre feature has been labeled an anti-tail, something that should not exist under the tidy physics we've relied on. Instead of debris being carried away, here appeared to be a luminous extension stretching directly sunward, almost as if the comet was defying the most basic laws of solar forces. Naturally, this lit a fire among conspiracy theorists. But before anyone jumps to alien technology or anti-gravity, let's slow down, because scientists do have a natural explanation for anti-tails, as strange as they appear. These illusions come from perspective and geometry. Picture a paper-thin sheet of dust particles spreading out from a comet. Look at it edge on, from just the right angle, and parts of that sheet may align with your viewpoint, creating the illusion of a jet pointing the wrong way. In reality, the particles are still behaving according to physics, but from Earth's position in space, they're projected onto our sky in a way that tricks the eye. Add to this Atlas's unusual orbital path, nearly retrograde, tilted about 5 degrees compared to the ecliptic plane, and the potential for strange perspective effects multiplies. Later, astronomers confirmed Atlas still produces a more traditional tail pointing away from the sun, captured in crisp detail by the Gemini South Telescope on August 27th. Yet by then, the damage was done. The strange geometry of its earlier plume had already cemented Atlas's reputation as a comet unlike any other. Specialized techniques like polarimetry, which analyzes how light scatters off dust grains, have since revealed further complexity in the comet's tail. Each layer of study only deepens the mystery. Polarization studies of Atlas's coma uncovered something striking. Instead of showing the basic, relatively smooth structures expected in most comets, the scattered light patterns suggested a deliberate complexity, dust and plasma organized in structured forms that standard comet tail models couldn't account for. Think of it like comparing a balloon to an origami figure, both made from the same material, but one is simple, smooth, and uniform, while the other is intricately folded and layered. The comet's architecture, in other words, isn't random. It's highly structured, though without any obvious mechanism explaining why. This, combined with the puzzling anti-tail and Atlas's odd orbit and velocity, created a spectacle that left even seasoned observers unsettled. To casual stargazers and some professionals, the comet appeared to rebel against the natural forces that have governed every object we've ever tracked in the solar system. And here lies the trap. When humans see something that seems to break universal rules, our minds instinctively leap to fantastical explanations. If the tail looks like it's resisting the solar wind, maybe, people speculate, it isn't a comet at all. Maybe it's powered by something else. While exotic interpretations grab the imagination, the truth in astronomy is usually subtler, though no less fascinating. The anti-tail itself is an example of that subtlety. It's not alien propulsion, it's geometry. Much like mirages or optical illusions here on Earth, what we see depends on perspective. A perfectly straight road under heat waves seems to bend and shimmer. Distant mountains can appear to float above the horizon when unusual air layers bend the light. And under the right orbital conditions, a comet can display features that look impossible while still obeying the known laws of physics. Atlas's orbit, running almost retrograde and tilted just slightly compared to the planetary plane, maximizes these optical distortions as viewed from Earth. As it continues its arc toward the sun, changing angles will shift which parts of its vast dust sheet are visible, hiding some sections while revealing others. creating new illusions of structure. It's like trying to guess the shape of an object just by watching its shadow dance on the wall. There's truth there, but it takes careful work to piece together the real geometry. And yet, even when accounting for perspective tricks, not everything can be brushed aside. Light polarization analysis shows Atlas's coma isn't just a puff of gas and dust. It's arranged in patterns far more complex than expected, hinting at processes we don't yet fully understand. This complexity made astronomers start using terms like unprecedented and without comparison. Atlas may resemble a comet, but the way it manipulates light marks it as something we've never seen in our skies before. Which brings us to part 5, the swarm. Autumn of 2025 has turned Earth's night skies into a scene right out of a cosmic traffic jam. Multiple comets are passing through the inner solar system at the same time, stacking spectacle upon spectacle in a way that hasn't been witnessed for decades. At the center of this drama stands 3I Atlas, an interstellar interloper, surrounded by more local visitors born much closer to home. The result is a rare confluence, a literal cluster of comets lighting up the heavens. Take Comet R2 Swan, for example. It swung around the Sun at its closest approach on September 12th, and will pass Earth on October 21st at just a quarter of an astronomical unit, about 23 million miles, close enough to potentially be visible with the naked eye, if skies are clear and dark. Then there's Comet 414P/Stero, a familiar periodic visitor that drops by every 7.5 years. It reached perihelion on September 27th at about half an AU, and trailing not far behind is Comet A6 Lemon, expected to peak at magnitude 3 or 4 when it slings past the Sun on November 8th. If predictions hold, Lemon's brilliance could shine brightly enough for city dwellers to catch, with only a modestly dark sky. But if so many comets suddenly appear at once, doesn't that suggest they're connected? Not really. The overlap is produced by orbital mechanics, not physical association. Imagine cars on highways headed into the same city from different directions. They aren't traveling together, they simply arrive around the same time, creating the perception of congestion. The clustering of comet appearances happens because they only become visible to our eyes when they're close enough to the Sun to ignite glowing comas and tails, and when they're in sky positions where Earth-based observers can see them clearly. It's a mix of orbital timing and observational perspective, not coordination. And comets weren't the only objects making headlines. Mid-September also brought an increase in asteroid buzz, with several near-Earth objects passing by in quick succession. None threatened Earth, but they played their part in building the tension-filled atmosphere of the month. The most discussed was asteroid 2025 FA22, which brushed past on September 18th at a few million kilometers distance. A safe passage, yet close enough to fuel plenty of news coverage and social media fear-mongering. Several smaller asteroids joined the parade, each briefly trending in headlines before disappearing from the cycle. To the public, all these space rocks and comets bunched into a few short weeks felt like an invasion, as though the heavens themselves were stirring. In truth, Earth encounters close passing asteroids on a fairly regular basis, although most go unnoticed. The heightened media focus this fall is less a spike in events and more a reflection of how sophisticated sky surveys have become, spotting and tracking many more objects than in decades past. It's awareness, not apocalypse. Still, perception matters. The human brain is wired to hunt for patterns, to draw connections, to spot meaning in the noise. When multiple bright comets appear and asteroids skim past within days of each other, it doesn't feel like coincidence. It feels like a sign. And throughout history, sudden gatherings of celestial bodies have been interpreted as omens, warnings from the gods, signs of upheaval, even markers of world-changing events. That instinct hasn't gone away. It simply clothes itself in new language today. For some, this swarm has sparked whispers of darker possibilities. If an advanced civilization wanted to send machines, probes, or ships into a solar system like ours, what better time to slip them through unnoticed than during a natural swarm of comets? Hiding artificial travelers among natural ones would create perfect camouflage. Our telescopes would register a crowd of glowing visitors, our brains assuming they were all alike, unless someone looked deeper. It's speculative, of course, but also chilling to think about. The cosmos already provides cover stories in the form of random orbital alignments, gravitational nudges, and cometary outbursts. If someone or something wanted to move quietly, a natural swarm would be the perfect time to blend in. A path that carries Atlas close to more than one planet is the kind of trajectory that makes mission planners sit up and take notice. This very course brings it close to Mars first, offering a chance to study the red planet from a unique new angle before it plunges deeper toward its encounter with the Sun. From a purely strategic perspective, if someone or something were using natural events as cover, moments like this would be ideal. The sky right now is full of comets, asteroids, and bright spectacles. That sheer abundance ensures the public and even professionals are distracted by multiple moving targets at once. A strange signal or an unusual behavior might simply disappear in the noise. Of course, the far more likely explanation is the ordinary one. The overlapping comet arrivals and asteroid passes represent the natural cycles of solar system dynamics, boosted only by our improving detection technology. Yet the oddities of Atlas make the question linger: is this a coincidence of nature, or are we watching something with purpose baked into its path? The stakes of that question only rise when we turn to one last set of measurements that refuses to conform to the usual playbook. The way 3i Atlas bends and polarizes light pushes it beyond easy explanation, edging some cautious scientists into uncomfortable conversations about what is natural and what might be otherwise. Which brings us to part 6, natural or artificial. The real question haunting astronomers in 2025 isn't whether Atlas is strange, that much is undeniable. It's whether its strangeness represents natural processes beyond our current models, or points towards something designed, something outside our expectations of interstellar visitors. To put it in perspective, rewind to the two cosmic guests that came before it. The first, Oumuamua, spotted in October of 2017, took astronomers by surprise. It arrived on a hyperbolic path, leaving no doubt it came from beyond the solar system, but showed none of the signs expected of comets. No coma, no tail, just a tumbling, elongated object passing silently through. Stranger still, it accelerated slightly as it moved away from the Sun, and gravitational models couldn't fully explain that tiny but real push. This left the scientific community divided. Could it be natural outgassing from ices we couldn't see, or something more, something alien? To this day, its true nature isn't settled, though most cautious explanations lean toward unusual but natural origins. 2 years later came Borisov. The second interstellar arrival was its opposite. No mystery tail, no bizarre acceleration. Borisov behaved exactly like a standard comet, complete with gas, dust, and a composition nearly identical to those found in our neighborhood. If Oumuamua was strange, Borisov was almost comfortingly ordinary. Now Atlas cuts right between them, and in doing so creates perhaps the deepest mystery so far. On one hand, it is definitely comet-like. The coma, the tail, the brightening, all the expected signatures are there, but the details resist categorization. A carbon dioxide, heavy chemistry unlike other comets we know, a rapidly inflating coma far outpacing predictions. Dust that polarizes light in ways no previous comet, asteroid, or object has ever shown us. This combination doesn't fit Oumuamua or Borisov. It's something new. One key puzzle is the nucleus itself. Hubble data capped its radius at no more than 2.8 kilometers, putting its diameter under 6 kilometers. Ground-based surveys narrowed it further to somewhere in the low single digits. In other words, Atlas is small. Certainly not the monster some early rumors painted it to be. But if it's so small, how are we seeing such an enormous coma and such extreme activity? A tiny body simply shouldn't have enough volatile material to sustain what Atlas is doing, unless either the materials are vastly more efficient at driving activity than the ices we know, or the internal makeup is fundamentally alien. This is where speculative talk about artificial origins creeps in. If an object is oddly small, strangely efficient, and unusually structured, then one interpretation, admittedly the exotic one, is that it's not a natural comet at all. A craft, a probe, or something designed could, in theory, explain the energetic displays without requiring mountains of ices. That's the appeal of the artificial hypothesis. But science resists that leap, unless absolutely forced. The guiding principle of Occam's razor is hard to ignore. The simplest explanation that fits the data is usually the right one. Before astronomers call something alien, they will exhaust every possible natural scenario, and there are still plenty of options to consider. Atlas may simply contain ices more volatile than we're used to, born in a frozen nursery far colder than our Kuiper belt. Its surface structure could allow gases to escape with unusual efficiency. A fast, unstable spin could fracture the surface, opening up reservoirs of fresh materials, or hidden internal stresses could cause constant cracking, exposing more volatile pockets. None of these explanations are fully proven yet, but all remain on the table. Then we come to the polarimetry data, the heart of the puzzle. When sunlight bounces off dust grains in a comet's coma, the scattered light doesn't just brighten, it picks up a twist, a polarization pattern that reveals incredible detail about the dust's size, shape, and makeup. For every comet studied until now, those polarization values have fallen into familiar ranges. But 3i Atlas breaks the script. Its numbers dip into extreme negative polarization at small phase angles, with minimum values around 2.7% at about 7 degrees. Nothing we've studied shows behavior like that. The implications are startling. Perhaps Atlas's dust grains are uniquely altered by exposure to interstellar radiation during their long voyage. Perhaps they contain exotic materials we don't see in local comets. And here's where speculation deepens. Some scientists have pointed out these polarization signatures don't just defy the natural catalogue, they look eerily similar to what one might expect from engineered surfaces or artificial composites. To be perfectly clear, the community isn't calling it alien. Most credible researchers remain cautious, posting papers and blogs stressing that extraordinary claims demand extraordinary evidence. The data are real, yes, but the interpretation remains open. And as of now, Atlas shows no evidence of transmitting signals, no proof of maneuvering or course correction, nothing that screams intelligence. Its trajectory, while unusual, is still dictated by gravity, not hidden engines. If it is technological, then it would represent a machine or relic far beyond human capacity, an artifact launched tens of thousands of years ago by civilizations older than humanity itself. And that possibility, however unlikely, is exactly why Atlas grips our imagination. It sits uncomfortably between categories, forcing astronomers to confront both natural possibilities they haven't yet modeled and the faint but lingering echo of something designed, something watching. If a civilization existed with the capacity to send probes or objects across interstellar distances lasting tens of thousands of years, their technology would be so far beyond ours it's nearly impossible to imagine. That's one way of looking at Atlas, an artificial construct drifting into our solar system. The other way, and the one most scientists prefer, is that Atlas forces us to expand our understanding of natural physics rather than rewrite it in terms of alien engineering. It's a comet that bends the rules we thought we knew but hasn't yet broken them beyond repair. More observations, months' worth or even years' worth, will be needed before the evidence settles on one explanation or the other. Whether Atlas represents an exotic natural anomaly or something extraordinary, the answer has implications that go well beyond astronomy textbooks. If by some chance it is artificial, it would be the first verified encounter with technology from another star system, a discovery that would permanently redefine humanity's place in the universe. But before we leap to that possibility, we have to entertain a third, equally fascinating option. Perhaps Atlas is not unique, but only one shard of something much larger, which leads us to part 7, the debris field hypothesis. Sometimes the most fascinating theories come not from invention, but from catastrophe. What if Atlas, along with other unusual objects arriving in our skies, are fragments from a massive event, an ancient system-shattering disaster that launched vast amounts of material into interstellar space? Scientists already know that debris fields can be cast out of star systems in several ways, each capable of hurling material with enough speed to traverse the void and reach other suns. Early planetary formation itself is among the most chaotic eras in a star system's life. Planets colliding, moons breaking apart, and pieces slingshotting into deep space. Our own solar system's history bears scars of that violence, with Earth's moon likely born from the impact of a Mars-sized body in its infancy. Another trigger is the gravitational chaos unleashed when two star systems pass close to one another. During those close encounters, planets and comets can be ripped from their original orbits and thrown into interstellar pathways. Simulations suggest this is not rare on cosmic timescales, meaning a steady trickle of ejected material has always been flowing between the stars. And then there are the more extreme options: planetary collapses, moon breakups, runaway heating, or tidal destruction near a parent star. These events could scatter debris in all directions at tremendous speeds, creating clouds of interstellar fragments like shrapnel from a galactic explosion. Atlas's chemistry may point to such an origin. Its composition, rich in carbon dioxide, suggests it formed in extraordinarily cold conditions far out from its parent star, regions where CO2 ice could survive untouched for geological ages. That hints at creation in the outer reaches of an alien system, perhaps inside a debris field that was blasted outward before the material could undergo the thermal and chemical transformations most comets experience closer in. Some measurements even show a faint reddish tint in its spectrum, the kind of coloration linked to objects that have spent millennia exposed to cosmic radiation. In our own backyard, distant Kuiper Belt and Oort cloud objects show similar colors after long exposure to space weathering. The unusual way Atlas polarizes light could also support this debris field picture. Dust grains forged under catastrophic conditions, blasted by collisions, altered by shock waves, or later reshaped by millions of years of interstellar radiation, behave differently from standard solar system materials. They scatter light in patterns we don't expect, producing the odd polarization signals scientists are now measuring, the same ones that make Atlas's coma appear more intricate, more structured than a simple glow. Now, does the timing of multiple bright comets appearing in Earth skies this year automatically mean they're from the same source? Not necessarily. Much of what looks like clustering is an issue of perspective. Improved surveys mean we're spotting faint objects that once slipped past undetected. Add in that 2025 is a solar maximum year, when the sun is at peak activity and comets naturally appear brighter and more dramatic, thanks to stronger solar wind interactions. Those factors amplify interest and make coincidences appear significant when they may not be. Still, if the debris hypothesis has weight, we might well discover more interstellar fragments in the near future. The Vera Rubin Observatory's all-sky survey, with its unprecedented ability to track faint fast objects, will likely reveal dozens or even hundreds more interstellar travelers in the coming years. To imagine how this works, think of a handful of confetti tossed from a speeding car. At first, the pieces stick close together, but over miles they spread out, each shard catching different air currents. Now scale that up to cosmic proportions. If Atlas was launched from a disaster millions of years ago, its siblings would now be scattered far and wide, occasionally passing through star systems like ours. Spotting connections between them would be nearly impossible, like trying to trace individual sparks from a firework long after it's gone off, with each spark drifting for years across the night air. So, what kind of evidence would confirm the debris hypothesis? Compositional signatures would be key. If multiple interstellar objects display matching chemical fingerprints that differ from local comets, that would strongly imply a shared origin. Velocity patterns offer another clue. If a set of objects can be traced back to a common trajectory or burst point, even roughly, that strengthens the case. Advanced simulations of ejection events could then be compared to the timeline and paths of real-world interstellar visitors, testing whether the predicted dispersal matches what we're beginning to see. And here's the most astonishing perspective. The timescales involved dwarf human history. Imagine if Atlas came from a planetary breakup that happened 10,000 years ago in a star system 50 light-years away. By the time the debris reached us, humanity would have gone from foraging the wild to building civilizations, completely unaware that somewhere out there, catastrophic violence had already launched pieces of a shattered world on trajectories that would one day pass through our skies. From that angle, the debris field scenario offers a compelling middle ground. It doesn't require alien technology, nor does it demand we invent new physics. It simply paints the galaxy as what it already is. A restless, violent place where worlds collide, stars disrupt each other, and fragments drift silently through the dark until, by chance, they find us. And that, in its own way, is no less extraordinary. Each fragment of material from another star system carries with it a kind of record frozen chemistry structural clues and radiation scars that tell the story of its birthplace and the violence that sent it flying into interstellar space. Studying that debris can reveal details about planet-forming environments and catastrophic events we could never hope to witness firsthand. But not everyone believes Atlas and its companions are simply cosmic rubble. There's another idea, one that takes the mystery in a very different direction. What if these strange arrivals, 3i Atlas included, aren't the accidental products of cosmic chaos, but deliberate emissaries? That brings us to part 8, the Scout Theory. Back in 1960, scientist Ronald Bracewell proposed a concept that has haunted the search for extraterrestrial intelligence ever since. Instead of sending fragile radio signals across unimaginable distances, what if advanced civilizations choose to send hardware instead? Autonomous probes that travel to nearby stars and quietly observe, collecting far more data than a simple broadcast ever could. These messenger probes, later dubbed Bracewell probes, would be like long-term robotic ambassadors, capable of waiting patiently in other systems for intelligent life to arise. Layered over this is the earlier notion of mathematician John von Neumann, self-replicating machines. If you combined Bracewell's observation probes with von Neumann's replicating capability, you'd have a system that could spread across the galaxy inexorably. Each probe could arrive in a star system, construct copies of itself using local materials, and launch them outward. Over millions of years, the galaxy could be laced with a quiet web of alien reconnaissance devices, requiring no direct broadcasts or centralized control. Now consider Atlas through that lens. What if this isn't a comet at all, but exactly the kind of disguised reconnaissance system Bracewell suggested? Its masquerade as a comet would be the perfect camouflage. It follows a natural gravitational path, blending seamlessly with the countless icy rocks and dusty bodies orbiting the Sun. From an observational stealth perspective, the strategy would be genius. Comets provide perfect cover. They brighten, they outgas, they sprout tails, and no one looks twice at them, until one, like Atlas, starts breaking the rules. Atlas's trajectory alone would make an engineer proud. It sweeps close to Mars, giving any instruments a chance to make observations there, then arcs deeper to offer views of Venus and Earth. It all happens during a solar maximum, exactly the kind of active period when an advanced probe could monitor how our civilization copes under stress. Satellites interfering with solar storms, power grids flickering, communications bending under the radiation. For reconnaissance, the timing couldn't be better. Some of the peculiarities could even make sense in this context. The strange brightness variations might not only be natural eruptions of gas and dust, they could be deliberate modulations, system checks disguised as flares. The rapid coma expansion could just as easily be interpreted as an artificial deployment of instruments, the cosmic equivalent of antennas unfurling, masked perfectly as cometary activity. The chemistry dominated by carbon dioxide is suspiciously convenient too. Codels is an efficient propellant for subtle adjustments, while also perfectly natural-looking as a cometary ingredient. A probe using CO Dull could perform delicate course corrections while still wearing the full costume of a dusty wanderer. Even the anti-tail geometry fits the theme. While geometry explains it naturally, the configuration also happens to be excellent for maximizing solar energy collection. If an object wanted to orient itself carefully toward the Sun, something simple in appearance could in fact be multitasking, feeding instruments, generating power, all while still convincingly imitating the complexities of comet physics. The polarization data remains the most eyebrow-raising connection to the Scout idea. No comet dust we've studied scatters light the way Atlas does. By contrast, engineered materials could very well produce unexpected optical effects. Think about advanced composites, radiation-hardened coatings, layered nanomaterials, things designed specifically to withstand centuries of cosmic radiation, or shield sensitive instruments from interstellar debris. Their optical scattering would look alien because it truly is unlike anything nature typically forms. Atlas's small size also plays into the narrative. A probe doesn't need to be a massive rock. In our own era, humanity already fits advanced instruments onto CubeSats the size of shoeboxes. Scale that up with 1 million more years of technological progress, and you could easily pack unimaginable capability into a body only a few kilometers wide. A tiny comet could in fact be a perfectly sized reconnaissance craft. Still, there are problems. Despite intensive monitoring, not a single artificial radio signal has been detected from Atlas. No course corrections beyond the pull of gravity have been observed. Its path, while peculiar, still adheres to known dynamical laws, no evidence of hidden engines or guidance systems. The sheer engineering required for a probe to cross interstellar gulfs, survive for millennia, and still function flawlessly dwarfs any benchmarks we can even dream of. And there's the puzzle of purpose. Why now? Our planet's radio and technological signatures have been leaking into space for less than a century, hardly a blink in galactic terms. For Atlas, perfectly timed to arrive during this adolescence, the coincidence feels almost too neat. Would a civilization advanced enough to send scouts require surface-level verification of what they could already deduce from afar, or does their timing have motives beyond what we can guess? Even with those counterpoints, the scout theory remains compelling. It reframes every anomaly, Atlas's brightness, its chemical weirdness, its optical puzzles, its geometry, into features that make sense under a cover mission scenario. Even more provocative, if Atlas is not alone, then the swarm of strange objects weaving through our skies this fall could represent a coordinated strategy, multiple probes watching us from multiple angles, blending with the crowd until their work is done. But here is the profound question this theory leaves behind. If the galaxy is seeded with civilizations advanced enough to pull this off, why have we not yet found undeniable proof? Why only hints, puzzles, and anomalies? Perhaps the answer lies in one of the oldest riddles of modern science, an enigma that has haunted every discussion of extraterrestrial life since it was first raised. Back in 1950, while having lunch at Los Alamos, physicist Enrico Fermi posed a deceptively simple question that still echoes across science today. Where is everybody? With billions of stars in the Milky Way, countless planets and immense stretches of time, it seems almost certain life should have arisen elsewhere, and yet not a shred of undeniable proof exists. This contradiction became known as the Fermi paradox, and it remains one of the greatest unsolved mysteries in modern science. A decade later, in 1961, astronomer Frank Drake introduced his famous equation, an attempt to put numbers to the paradox by multiplying together probabilities. How many stars have planets? How many planets might host life? How often that life becomes intelligent? And how long those civilizations may last? Even when filled with conservative estimates, the equation suggests our galaxy should contain thousands of advanced societies. With 400 billion stars to work with, the silence still feels deafening. This is where interstellar visitors like 3i Atlas change the conversation. Each time one of these cosmic travelers enters our skies, it acts like a sample capsule from another solar system. Every bit of gas it carries, every trace of dust, every chemical fingerprint encodes information about its origin. Atlas's bizarre carbon dioxide, rich makeup for instance, suggests it condensed in a region so cold that CO highs could survive intact for eons. That tells us about the diversity of planetary systems elsewhere, and it hints at just how widespread the raw ingredients for life might actually be across the galaxy. But Atlas's oddities also provide data that spill into deeper questions. If advanced civilizations do exist, maybe they're smart enough to use this kind of debris as camouflage. Blending probes into natural comet swarms would be the perfect strategy. After all, no one looks twice at a comet, and right now, the autumn skies are brimming with them, providing cover for anything that wanted to remain hidden in plain sight. This would mean the solution to the paradox is chillingly straightforward. Extraterrestrials are already here, watching quietly, slipping between natural events. They wouldn't announce themselves with a display of spacecraft. They wouldn't risk panic or confrontation. They'd slip in silently among the comets. Of course, there's still the other view. Natural explanations remain firmly on the table, and scientists lean toward them. Atlas might simply be a comet with unusual chemistry, shaped by physics we haven't quite grasped yet. The clustering of comets in 2025 could be nothing more than celestial coincidence, amplified by better telescopes and surveys than we had even a decade ago. Occam's razor reminds us the simplest solution is usually the right one. Strange outgassing, odd plasma behavior, exotic chemistry. These are all natural expansions of known science, requiring no aliens at all. Still, the match between the anomalies of Atlas and the requirements of a long-duration reconnaissance probe is hard to ignore. Interstellar missions would demand rugged, simple systems that can endure for millennia. They would need stealth designs cloaked as natural phenomena, capable of adjusting trajectories subtly while taking full advantage of gravitational routes. The resemblance is uncanny enough that while scientists resist the leap, the idea continues to lurk in the background. The real sticking point is timing. Why now? Humanity has been leaking radio and radar signals into space for less than a century, a blink in cosmic terms. Our satellites and infrastructure are only decades old. By some extraordinary coincidence, interstellar visitors show up exactly during this fragile adolescence of ours. Is that sheer chance or response? Perhaps probe arrivals are simply routine, not aimed specifically at humanity. Maybe civilizations send scouts regularly to nearby stars as part of a long-term survey. Or perhaps our signals, nuclear tests, radar bursts, communications satellites, are much brighter and more detectable across interstellar distances than we realize, drawing attention sooner than we'd expected. It could even be that we've been looking in the wrong way all along. SELTI has trained its ears for radio signals, expecting voices in the void. But what if civilizations rarely broadcast, and instead rely on probes silent and enduring, sweeping into star systems like ours to investigate firsthand? Atlas could represent the better question, not where is everybody, but have they been here the whole time, and we simply didn't recognize them? Whether Atlas proves to be natural or artificial, the outcome will reshape our place in the cosmos. If it's natural, then interstellar debris is more common than we thought, opening new windows into how other systems form and evolve. If it's artificial, it changes everything. The paradox dissolves instantly, not through silence but through subtlety. Civilizations might exist, but their intelligence lies in avoiding attention, blending into the background of the galaxy, while studying us without interference. That possibility is as unnerving as it is profound. And this takes us directly to part 10, alien invasion or cosmic coincidence. As Atlas barrels toward the inner solar system, the debate has escalated into territory that once would have sounded absurd. The evidence is still inconclusive, but the stack of anomalies has forced serious scientists into conversations they never thought they'd have. On one side are the comet specialists, researchers who have studied these ice balls their entire careers. To them, Atlas is strange but still natural. Exotic volatiles drive the brightening. The anti-tail geometry comes from perspective tricks and uneven dust patterns. The polarization quirks stem from grains shaped unlike anything yet catalogued, but still products of physics. They emphasize the golden rule: extraordinary claims demand extraordinary proof, and so far that bar hasn't been crossed. Yet on the other side, a rising number of voices find the coincidences too heavy to ignore. The arrivals, the timing, the clustering, so much celestial activity packed into one short season looks less like randomness and more like choreography. And Atlas's glowing green veil, its unusual tail geometry, its runaway coma growth. The combined spectacle feels almost designed to draw attention upward. To the conspiracy-minded, the question isn't whether this is coincidence, it's whether something out there wants to be seen. Why would so many strange celestial objects appear within the same tight window of time, unless perhaps their arrival had been coordinated? Mid-September brought both unusual asteroid activity and comets behaving in bizarre, visually dramatic ways. Together they create a story that feels almost too neat, a narrative unfolding with precision that seems designed rather than random. But here's the critical reality check. Whatever 3i Atlas is, it poses no physical danger to Earth. Its closest approach will happen on December 19th when it passes a safe 1.8 astronomical units away, around 170 million kilometers. That's farther than the distance between Earth and our Sun. Even if Atlas were under perfect artificial control, its trajectory contains no path that brings it anywhere near striking our planet. What it will do is make stunning encounters. Atlas will sweep past Mars, Venus, and even brush cosmic shoulders with Jupiter, close only in astronomical terms, still separated by tens of millions of kilometers. But the sheer spectacle of its glow, its twisted tail geometry, and its runaway brightening triggers something deeper than numbers. The way it looks pulls us into associations we've been trained to expect by culture and science fiction. A glowing emerald haze, a tail pointing in forbidden directions, unpredictable surges of brightness. All of it maps perfectly onto visions of alien phenomena we've absorbed for decades through movies, novels, and television. Our brains are conditioned for the dramatic. Popular culture suggests if aliens arrive, they'll broadcast clear signals, blast across the skies with obvious craft, or declare their presence in ways no one could mistake. But the true reality, if reconnaissance were the goal, might be infinitely quieter. The smartest strategy would be to avoid setting off alarms, to camouflage as something perfectly ordinary while performing close study. A disguised visitor hidden among countless natural comets could achieve exactly that. In fact, the very debate around Atlas might be the goal: stir curiosity, ignite speculation, fuel conversations, all while never confirming anything outright. Ambiguity buys time. Ambiguity prevents panic. Still, the timing haunts this conversation. Scientists pointing toward natural explanations emphasize an important factor: humanity's detection power has never been sharper. Modern sky surveys, amateur networks, and space observatories mean we're discovering far more objects and analyzing them in much greater detail than we could in past decades. What once would have slipped by unnoticed now dominates news cycles. In this view, the clustering of strange comets and asteroids is largely an artifact of better technology and heightened awareness. It's not that the cosmos is more crowded, it's that we finally noticed. But supporters of the more exotic interpretation press back hard. They note that interstellar objects should be exceedingly rare, and yet we've found several within a short time. Combine that with brilliant comets' green flares in the sky, and asteroids buzzing Earth like cosmic flies, all during the same narrow period, and the odds against coincidence grow thin. If you were looking to stage covert arrivals in our system, they argue, you couldn't ask for a better smokescreen. Professional astronomers, at least publicly, tread carefully. Official statements remain cautious and highly conservative, focused on technical descriptions, how brightening curves plot, how dust polarizes light, how models may need adjustment. Behind the scenes, however, many quietly admit Atlas is testing the edges of our theories. The polarization readings especially are so out of step with anything measured before that astrophysicists are struggling to reconcile them with existing physics. To fit them cleanly within normal requires assumptions stretched past comfort. Meanwhile, the institutions themselves face their own challenge. Silence from major observatories in September has fueled more conspiracy fuel than any anomaly Atlas displayed in the sky. Where are the high-resolution images we should be seeing every week? Why did the flood of new public data suddenly stall? The record shows the Hubble Space Telescope last released a detailed image of Atlas back on July 21st. It revealed a nucleus tightly wrapped within its glowing dust shroud and gave crucial size measurements. Since then, nothing. Webb released groundbreaking infrared data on August 6 that made headlines when it confirmed Atlas's unusual carbon dioxide dominance. But after that, the well went dry. Nothing new, no fresh images, no updated spectra. The Gemini South Observatory published one spectacular photograph on September 4th, but even that was based on data from August. For conspiracy-minded observers, the timing seems suspicious. Why would the biggest telescopes on and above Earth suddenly go silent just as Atlas entered its strangest, most dramatic phase? For scientists, the answers are more mundane. Space observatories are booked months or years in advance, balancing complex schedules. Many instruments can't point too close to the sun without risking catastrophic damage, exactly the problem as Atlas plunges deeper toward perihelion. Solar elongation restrictions limit safe viewing, forcing astronomers to wait until conditions improve. Then there's the issue of proprietary periods where newly gathered data remains private for months before public release, a standard practice in the research community. Yet, timing matters, and when silence coincides with intrigue, doubts rush to fill the void, because what if the telescopes did capture something unusual, something unexplainable, and gatekeepers decided the public wasn't ready to see it? This is where the conversation shifts from science to disclosure. Imagine the implications if Atlas were confirmed to be more than natural: religious upheaval, economic turmoil, governments scrambling to rewrite policies overnight. From that perspective, A slower reveal through careful scientific debate gives society time to acclimate, a way to prepare us gradually rather than ignite chaos with an abrupt revelation. And that brings us to the next unsettling question, one whispered more and more by those following Atlas's story closely. If all these observations are being made, where exactly are the images we should already be seeing? Part 11. Where are the images? The observation timeline makes the absence stark. Amateurs around the world are flooding social media with dazzling photos, green-tinged halos, twisted antitails, the whole strange show captured nightly. Meanwhile, the facilities with the sharpest eyes, the ones capable of showing Atlas in unprecedented detail, have gone dark for the most critical stretch of its inbound journey. Under usual circumstances, this lag might barely raise notice. But here, under the weight of everything else, Atlas represents. Every missing image feels like a gap deliberately left open. When professional astronomers claim exclusive use of data before releasing results, it's not evidence of secrecy, it's how the system works. Research teams who request telescope time usually get first access to the results they collect, giving them months to process the data, publish papers, and guard the effort they invested before it becomes public. Raw telescope data itself isn't easy to pass along instantly either. It has to go through weeks of calibration, correction, and analysis before it can be translated into meaningful science. On top of that, there's huge competition for viewing time on instruments like Hubble and Webb. Every month they receive far more observation requests than they can realistically approve, forcing difficult decisions about which cosmic mysteries take priority. 3i Atlas, strange as it is still just one of many competing targets. And yet, despite these completely reasonable explanations, the absence of September data still seems suspicious to many. That's because September wasn't just any month in Atlas's journey, it was the moment the comet made its most dramatic lurches away from prediction. It was when its brightness suddenly deviated from projected light curves. It was when its eerie green glow started dominating photographs. If governments or space agencies had picked up on something extraordinary, this is exactly when they might lock down details and run their own private analyses. A gap at this precise moment looks more deliberate than coincidental. Into that vacuum rushed amateurs. In places like Namibia, Chile, and Australia, under dark skies, backyard astronomers with advanced cameras are capturing Atlas in detail nearly every night, posting image after image to social media. The photos are spectacular, showing the intense green cloud, bizarre tails, and the comet evolving week by week. But while gorgeous, these images can't match the power of professional instruments. They can't extract chemical fingerprints from spectra. They can't measure polarizations at the precision needed to test theories. They can't reveal hidden internal chemistry. That contrast between an explosion of amateur visuals and a suspicious silence of professional releases makes the missing data stand out more sharply. Normally, September should have been the golden window for observatories to lock in treasure troves of data. This was when Atlas's unusual brightening spiked, when the green fluorescence intensified, when even its changing antitail geometry would have been most fascinating to measure. Instead, the official logs show a void right where the most interesting things were happening. To those inclined towards suspicion, it looks like a pattern engineered to amplify speculation, as if someone wanted curiosity to boil over without offering definitive answers. International astronomy usually thrives on collaboration. Data sets are shared, leaks happen, and preliminary results spread quickly through professional networks long before they reach the public. The fact that nothing from September has appeared anywhere, neither formal nor informal, suggests one of two possibilities. Either no observations exist, or what does exist is being tightly controlled. The expected excuse is that a major observational blackout is coming anyway. And that is the next piece of timing conspiracy theorists seize upon superior conjunction. Astronomers know it as a predictable obstacle, but skeptics paint it as the perfect cover story. In October 25, 3i Atlas will swing behind the Sun from Earth's point of view. During this alignment, the comet becomes engulfed in the solar glare, vanishing from all Earth-based observatories. Even space telescopes can't risk looking so close to the Sun without threatening billion-dollar equipment. And as fate would have it, that conjunction lines up almost perfectly with Atlas's most explosive period, perihelion, its closest pass to the Sun, when comets usually stage their most dramatic activity. Science explains this as simple celestial geometry. On October 21st, with the new moon, Atlas hits minimum solar elongation, meaning it's in the worst possible position relative to the Sun's blinding light. For weeks it will be hidden from view, with peak outgassing and tail activity happening entirely behind the curtain. By the time it emerges in late November, much of the most spectacular action will already be over. From a purely observational standpoint, this is frustrating but natural. High brightness from the Sun obliterates faint signals like those from Atlas, making it nearly impossible to capture useful information. It would be like trying to photograph a tiny candle while staring into a stadium spotlight. Protection protocols on instruments like Webb, Hubble, and others also make pointing near the Sun completely off limits. None of this is new. It's essential safety procedure. But through the eyes of conspiracy watchers, it's a suspicious stroke of luck. If someone wanted to hide what Atlas truly is, they couldn't ask for better cosmic timing. Just when the comet should be at its strangest, it disappears from the stage. Still, conjunction doesn't wipe it out for everyone. A fleet of space probes scattered through the solar system will maintain angles unaffected by Earth's line of sight. The SOHO spacecraft, dedicated to watching the Sun, might catch glimpses of Atlas skimming by. NASA's twin stereo probes, stationed ahead of and behind Earth's orbit, could see activity from different perspectives. The European Solar Orbiter, operating in a tilted orbit above the ecliptic, could also offer unique angles less impacted by conjunction glare. And then there's Mars. As Atlas brushes relatively near the red planet in early October, orbiters like Mars Reconnaissance Orbiter's HiRISE camera, ESA's Cassis on the ExoMars orbiter, and Mars Express's stereo camera all plan opportunistic snapshots. These spacecraft, unconstrained by Earth's sunward perspective, could capture data that fills the blackout gap. The real question is whether those spacecraft images will ever reach us publicly, or whether they'll join September's Earth-based silence in some classified archive. Because when we look back, the critical window of Atlas's story, the moment it flared brighter, greener, stranger than the rules allow, will have happened mostly in the dark, when our greatest telescopes pointed away. The upcoming Mars flyby represents the last opportunity for truly high-resolution images before 3i Atlas slips into the observational blackout of superior conjunction. During this encounter, spacecraft orbiting Mars will be able to study the comet from much closer ranges than any Earth-based telescope could achieve. Data from this flyby should reveal critical details about the nucleus, the expanding coma, and the dynamics of its bizarre tail structures. Normally, findings from missions of this significance would be shared quickly through both scientific publications and official space agency channels. If those images show anything extraordinary, or even confirm suspicions raised by Atlas's unusual chemistry, then we should expect to see those results within weeks, if not sooner. But this critical period aligns with another celestial complication. The Sun's approach to solar maximum in its 11-year activity cycle. Surges in solar wind, powerful coronal mass ejections, and heightened electromagnetic interference will all coincide with Atlas's closest approach to the Sun. For comets, this means fireworks tails cut off abruptly by solar eruptions, dramatic fluctuations in brightness, and highly unstable plasma effects. These natural solar-comet interactions could, ironically, blur the line between the expected and the inexplicable. If Atlas were equipped with anything artificial, sensors, propulsive systems, communication equipment, these wild solar conditions would provide the perfect camouflage, masking any unusual emissions or maneuvers behind the chaos of solar physics. The real test will come after conjunction, when Atlas finally re-emerges into the dawn sky by late November. That moment, visible to observers in both hemispheres, will deliver the first decisive clues about its hidden evolution. If it returns looking dramatically different, its brightness amplified beyond models, its tail orientation altered in ways physics can't easily explain, it will be hard to dismiss exotic explanations. If instead Atlas reappears as a textbook comet in post-perihelion decline, with brightness levels dropping predictably and its debris trail behaving as expected, the scales will tip firmly toward natural explanations. December 19th, when Atlas makes its closest approach to Earth at a safe 1.8 astronomical units, will mark the final act of the story. At that stage, professional observatories will be able to observe it again without solar interference, while amateur astronomers across the world are already preparing coordinated observation campaigns to ensure nothing is missed. These grassroots observers, scattered across continents and connected by online platforms, may serve as the most transparent witnesses of Atlas's fate. Their work could provide the world with vital data even if official observatories continue their pattern of silence. But this is about more than telescopes and trajectories. The period of conjunction itself has become a kind of experiment, not just in astronomy, but in how information is managed. How agencies choose to share, release, or withhold data during this blackout will reveal their priorities as much as the comet's behavior reveals its physics. If Atlas is natural, then this is simply a frustrating but ordinary case of bad timing. But what if it's not? If Atlas does conceal technologies or anomalies too disruptive to reveal casually, conjunction offers a perfect cover weeks of secrecy under the shield of solar glare, when sensitive spacecraft could collect private measurements without a shred of public visibility. In such a world, the shift from science to national security concern would be swift and almost inevitable. Classified analyses would replace open publication, and details could remain buried for years or decades. Of course, there may be no conspiracy at all. The simplest answer is also the most disappointing. September's silence and October's blackout may simply rob the world of seeing one of the strangest comets in modern history at its most dramatic moment. When it finally returns to view, we'll find out whether it confirms the mundane or births a revolution in how we think about interstellar visitors. But what strikes many as uncanny is how perfectly this situation mirrors the plot of a movie designed as satire, rather than prophecy. Back in 2021, audiences watched the Netflix film Don't Look Up, a dark comedy built around the absurd mishandling of a comet on a collision course with Earth. The story skewered political dysfunction, corporate greed, and media circus culture, showing how humanity could ignore an existential threat, even when it was plain in the sky. It was intended as allegory, not prediction. Yet, as 3i Atlas grips both experts and the public, the parallels have become difficult to dismiss. In the film, astronomers struggle to make the public care about an incoming disaster, as officials manipulate the information and media personalities reduce the crisis to sound bites and spectacle. Billionaires exploit the threat for profit, and news outlets treat impending extinction as entertainment. Compare that to today, where Atlas's bizarre signals are layered through bureaucracies, professional caution, and fragmented communication that leaves ordinary people piecing together truths from scraps. Instead of clarity, we're fed an endless loop of speculation, rumor, and silence. Of course, the key difference is critical. Don't Look Up centered on a comet destined to annihilate Earth, while Atlas will pass a safe 170 million kilometers away. No matter its true nature, no one is in physical danger. Its orbit has been calculated precisely. Its Earth flyby distances confirmed repeatedly. There is no impact scenario, and unlike the fictional comet that gave humanity just months to prepare, Atlas has been tracked for more than a year, leaving no uncertainty about its safe trajectory. Still, the psychological parallels remain chilling. Social media brims with arguments: natural versus exotic, alien probe versus cosmic rock. News coverage flips between sober science and sensational headlines, inflating fears while neglecting context. The exact dynamic the film satirized, scientists trying to deliver careful messages while spectacle and politics drown them out, is playing out in real time. One of the most prescient aspects of the film was how quickly people adjusted. Something once unthinkable, an extinction-level comet, became another background story, competing with celebrity scandals and partisan squabbles, and in our world, Atlas, for all its strangeness, risks the same fate. Extraordinary, possibly history-changing evidence can be reduced to just another comet once the headlines move on. 3i Atlas now risks the same fate as the comet in Don't Look Up, its firestorm of attention slowly fading into background noise as the conjunction hides it from our view. The timing couldn't be better for normalization. Once it slips behind the sun, Atlas vanishes from public sight, becoming easier to dismiss as just another comet, rather than confronting it as the potential anomaly it might truly be. The movie's central conflict, respect for cautious scientific expertise battling against sensational narratives, feels eerily familiar here. On one side are sober astronomers urging patience and method. On the other, more dramatic voices win the public's imagination with stories of alien probes and hidden agendas. But the value of Don't Look Up isn't in predicting specific events. It's in showing how institutions often mishandle information that doesn't fit neatly into political or economic boxes. The same warnings resonate loudly with Atlas. The absence of recent images from the telescopes best equipped to study it, paired with the inconvenient timing of a sun-imposed blackout, creates an aura of secrecy that fuels speculation. Perhaps the gap is harmless scheduling. Perhaps it is a cover story. Either way, the silence worsens trust in institutions that desperately need credibility. Add to that a public increasingly desensitized to comet sightings, asteroid flybys, and space-close shaves. Many people treat sky events as spectacle instead of opportunities to deepen our grasp of the universe. Just as the film satirized, repetition breeds numbness. Extraordinary events become memes, headlines, or distractions, not subjects of collective urgency. Don't Look Up warned that humanity's weaknesses lie not in cosmic threats but in our inability to process complexity or to act together on timescales longer than a news cycle. 3i Atlas is now testing whether we've learned any better. Thankfully, the comet poses no existential threat, unlike the doomsday rock in the film. Still, the way it is handled becomes a live demonstration of whether scientific institutions, governments, and media can communicate honestly when faced with genuine ambiguity. The ending of Don't Look Up, when the comet strikes despite warnings, was ultimately about trust, how badly things collapse when institutions sacrifice credibility. With Atlas, we stand at a crossroads. We have a chance to show that transparency and balance are still possible, even with anomalies that test our models. But secrecy, suppression, or over-sensationalism could squander that opportunity and reinforce the very dysfunction the film satirized. And this leads to speculative territory that grips audiences most. What if Atlas is stranger than we dare guess? Part 14, Doomsday Speculations. What follows is not scientific prediction but imaginative exercise, worst-case thought experiments born in the space where science meets human fear. Atlas's data does stretch existing models, yes, but nothing currently suggests danger to Earth. And yet, our imaginations are wired to fill in the blanks with peril. The same instincts that helped our ancestors anticipate predators now spin shadow scenarios about hostile visitors when the skies act unnaturally. What if Atlas's true nucleus is larger than our measurements suggest? Current constraints, built on Hubble readings and ground-based surveys, put its radius under 3 kilometers, but those figures assume specific reflectivity and geometry. If Atlas's surface is unusually dark or its shape bizarre, our methods could be tricking us. A bigger nucleus would naturally explain its massive coma and brightness anomalies. Still, this flies against multiple independent measurements and consistent modeling. For it to be true would require systematic error across several major methodologies, unlikely but unsettling to contemplate. What if the Mars flyby triggers a fragmentation event? Comets are fragile. Under stress from heat or gravity, they sometimes split apart explosively, exposing hidden reservoirs of volatile ice. These events produce abrupt boosts in brightness and rapid coma growth. Atlas, brushing near Mars, could undergo just such a rupture. If fragments peel away, astronomers would detect trajectory shifts within days. It's plausible, but so far, orbital calculations have found no significant deviations. What if Atlas's path itself is subtly manipulated? Our modern astrometric data is so precise that Atlas's position can be projected months in advance with almost uncanny accuracy. Outgassing and rotation already produce small, predictable accelerations, but larger deviations, beyond what physics predicts, would require propulsion-like effects. If they existed, they'd have to be carefully tuned to avoid detection, hidden in the noise of natural comet emissions. Nothing concrete in the data yet points that way, but the suspicion lingers. What if Atlas isn't traveling alone? Could it shed reconnaissance payloads, tiny satellites cloaked as natural meteoroids? Such probes could, in theory, enter atmospheres, survive re-entry, and settle quietly on a planet's surface, feeding data back invisibly. The technology would need to be extraordinary, hundreds of years ahead of our own. But if a comet carried such riders, Their traces, fireballs, or meteor streams behaving unnaturally would almost certainly be noticed by the sensitive fireball networks that already cover the Earth. So far, no anomalies like that have been reported. Could the mid-September asteroid wave be connected? Several asteroids passed uncomfortably close to Earth's neighborhood just as Atlas began flaunting its strangest features. To some, the clustering looks like reconnaissance cover, multiple visitors entering the inner solar system together. But asteroid near misses happen all the time, and our detection systems have become far more thorough than ever before. The clustering was likely statistical noise amplified by heightened attention. Still, solar maximum adds even more drama. During this peak period, solar storms can rip comet tails away entirely, brighten them without warning, and play optical tricks that confuse even veteran observers. Atlas, caught in this stormier solar environment, could flare and twist in ways that look engineered when they're simply the chaotic signature of our star at its angriest. And yet, the overlap is uncanny. A strange interstellar comet at its wildest collides with the Sun at its most active, all while institutional silence deepens and speculation boils. This is where nightmares and imagination meet science, creating a stage that looks suspiciously like it was scripted. Whether that script is natural dynamics or something else entirely remains the question at the heart of 3I Atlas. When the Sun erupts with coronal mass ejections, the blast of high-energy particles can rip comet ion tails apart, sometimes snapping them clean off or producing sudden bursts of brightness that look shocking to anyone watching through a backyard telescope. Events like these are dramatic, but they're a normal part of comet behavior during periods of high solar activity. Physics explains them perfectly, and while they may look strange, twisting, flaring, or reshaping tails in seconds, they pose no threat beyond the kind of space weather our modern technology is already designed to endure. If anything genuinely hazardous were hidden in Atlas's journey, international monitoring networks would sound the alarm immediately. The Minor Planet Center, NASA's Center for Near-Earth Object Studies, and the European Space Agency's independent systems all track these objects around the clock, cross-checking each other's calculations to rule out collision threats. If a danger existed, humanity would not hear about it through rumors. It would be formally announced. That doesn't change the pull of doom-laden speculation. Our psychology gravitates toward catastrophe, especially when we're confronted with things mysterious, foreign, or poorly understood. Interstellar visits like 3I Atlas feed those instincts, marrying uncertainty with imagination. But place the facts side by side, and the sobering reality is clear. Atlas's orbit keeps it at safe distances from every planet. Its physical properties still fall within ranges. Science can stretch to explain. Its incredible behavior can fit within rare but natural possibilities. The wisest perspective is caution balanced with awe, because Atlas isn't just a spectacle, it's an opportunity. This comet carries a sample from another star system, a gift from interstellar space that opens windows on environments and conditions we would never otherwise touch. Whether natural or not, every particle of dust, every flicker of light, is new information about the universe beyond. And yet, even after setting aside the stories of doomsday impacts or secret probes, Atlas still refuses to settle into the ordinary. One aspect, one trio of anomalies has guaranteed its place as the strangest object humanity has ever observed. Call this Part 15, the alien look of Atlas. 3 characteristics set this comet apart. Each one alone is enough to demand study, but together they form a picture so unusual that it seems almost staged to test us. First, the brightening. In mid-September, Atlas began to shine faster than models said it should. Astronomers have long trusted brightness curves as one of the most solid predictive tools in their arsenal, based on how cometary ice normally sublimates into gas as sunlight warms it. Atlas violated those rules openly. Its climb above expected values wasn't a subtle wobble. It was a departure so blatant even amateurs noticed their sky charts failing. Suddenly, everyone from hobbyists to professionals was recalculating, doubting whether our comet models really apply to objects forged outside the solar system. The second extraordinary feature lies in its massive atmospheric bloom. Atlas's coma, dominated by carbon dioxide, isn't just big, it's absurdly big, extending hundreds of thousands of kilometers across space. James Webb's infrared data showed chemical balances never seen before in our local comets. Its CO-heavy fingerprint suggests an origin in conditions unlike anything familiar, maybe from a system far colder or more volatile than ours. The scale of gas production is so vast that it forces the unsettling question: how can a small nucleus sustain an envelope this large without exhausting itself? And then comes the crown jewel of strangeness: the polarization readings. Polar emissory is like a lie detector for dust. By studying the way light waves scatter as they bounce off tiny grains, astronomers can infer size, shape, and even texture. Every comet studied before has produced results within a recognizable range. Then came Atlas, with extreme negative polarization values around 2.7% at just 7 degrees phase angle. It instantly broke the pattern. Nothing in our solar system has registered these kinds of signals. To scientists, it feels like dust made of something we've never seen, something altered by exotic environments or carrying textures not produced by natural solar system chemistry. To more imaginative minds, it sounds like the fingerprint of artificial material. When you place all three together, the unnatural brightening, the oversized carbon dioxide coma, and the bizarre polarization measurements, the comet starts to feel like an object designed to confound us. Add in the visual drama of its ghostly green glow and impossible tail geometry, and you start to see why people say it looks alien. This isn't a casual impression, it's backed by measurements that resist easy explanation. And yet, here's the paradox at the heart of it all. Atlas is absolutely harmless to Earth. Even at its nearest on December 19th, it will remain 170 million kilometers away, safe, distant, untouchable. Its encounter with Mars on October 3rd will be an astronomer's dream, not a planetary threat. The only true danger Atlas presents is how it unsettles our sense of what comets and interstellar objects should look like. Its timing, vanishing into conjunction just when we need it most, tests not only our science but our systems of communication and trust. So where does this leave us? Some insist that with enough stretching, natural processes can still cover every anomaly: unusual ices, strange surface textures, exotic but natural dust. It's possible. Others argue the mounting oddities have pushed past coincidence into something else. Evidence, perhaps, that we are not just observers of the universe but subjects of someone else's study. Either way, Atlas is a frontier, a line where old assumptions break. The comet now stands as either the most peculiar natural object ever to enter our skies, or the first undeniable sign that intelligence and technology operate on scales far beyond human reach. As it swings towards perihelion, every single observation becomes a data point in humanity's greatest question. By late November and into December, when it finally emerges from behind the sun's glare, we may find clarity, or we may find more mystery. Because the closer Atlas gets to the sun, the more alien it looks. The question that hangs over the world is whether that alien look reflects physics we've never encountered, or proof that we are not alone, and someone else has been watching all along.